Okay, so let's talk a little bit about cylinders and quadric surfaces. Okay, so this is a follow-up to, this is, by the way, section 12.6, and it's a follow-up to the uh, two types of surfaces we've already looked at. We've looked at planes and we've looked at spheres. Okay, and so we had general formulas for the equation of a sphere. Do you remember that? So a sphere centered at x naught would be like x minus x naught squared plus y minus y naught squared plus z minus z naught squared equals r squared. So that's a general formula for a sphere. And then we had several different variations of formula for a plane. And I'll just put them here just as a reminder. So we had our vector form, which is n dotted with r minus r naught equals 0. Or we could have a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Okay. So today, or in this lecture, we're going to look at cylinders and quadric surfaces. Okay. And the main way we're going to do it two different ways. And the first way is to look at traces, aka cross sections. And so basically, what is a cross section? Think about, for instance, if you had an apple, so say this is your good old juicy apple, and if you slice, that's another word for this is a slice. If you cut the apple or you slice the apple, right? Imagine if you just slice the apple, and then what would it look like? Right? Maybe it looks like that. This would be a cross section of that surface. So, kind of just to make sure we're on the same road, on the same track here, imagine if you had a cylinder like this. If you take cross sections that are like this, what does a cross section look like? The answer would be cross section is going to be a circle. But if you take a cross section that is lateral, I guess that would be considered a lateral cross section, what would that look like? That would be a rectangle, right? So by taking a bunch of cross sections, you can actually build up your original surface. Okay. And taking cross sections corresponds to holding one of the variables in your equation constant. Okay, so first let's look at cylinders. So a cylinder is a surface that consists of all lines that are parallel to a given line and pass through a given plane curve. Okay, so let's sketch the graph of the surface z equals x squared. And one of the things it says is notice that the equation of the graph, z equals x squared, has nothing to do with y. Okay, so now let's see here. So what is a way to approach this? So if we wanted to sketch z equals x squared, here's what we could do. In order to sketch z equals x squared, let's see here. So we say what happens when y equals 1? So if y equals 1, so in terms of our picture here, this is asking like what happens if we look at the cross section that is going through here, right? Because this is the plane y equals 1. So we're just coming, sorry, we're 1 unit out, right? 1 unit to the right. Well, if y equals 1, then we've got z equals x squared. So it looks like that. It'll be a parabola, right? And what about when y equals 2? We'll have the same thing. We'll have another parabola. And y equals 3, we'll have another parabola. And we just, what if y is negative? We're still going to have more and more parabolas. So each cross section that we take that is parallel to the xz axis is going to be just a parabola. So we end up with this type of surface. So it's just a parabola. Does that make sense? We should have some better pictures here. Yeah, there we go. Okay, so this is called a parabolic cylinder, and it's made up of infinitely many shifted copies of the same parabola. Okay, and here the rulings of the cylinder are parallel to the y-axis. Okay, so you can see here the kind of, this is the cross section.
It's 22:45.
Thank you. So each cross section is a parabola. Okay. Now this is very key. So just like here, when we had z equals x squared, we had a cylinder, and it was based off of this idea here is if we had x and this is z, then we know back from 2D space we would sketch this parabola as equals x squared. But because we're in 3D space, you kind of have to let that, right, it's kind of like you can,
It's 10:45.
Thank you. You want to let that, you want to keep the fact that z is equal to x squared, but bring that through infinitely many possibilities for y, if that makes sense, right? And here, if you have x squared plus y squared equals 1, well, now we know that that's a circle centered at the origin, radius 1, if this is x and this is y. But now, imagine adding z, right? So now once we add z, you're going to take that circle and you'll have like infinitely many. So what you end up with is a cylinder. Does that make sense? Where like here's x and here's y, and coming up here is z. Okay, so you want to remember that it's not a circle in 3D space, it's actually a cylinder, but each cross section is a circle. Okay. And now quadric surfaces. A quadric surface is a little more complicated. So you can have second degree coefficients for second degree variable in x, y, and z. Quadric surfaces are the counterparts in 3 dimensions of the conic sections in the plane. So remember we had conic sections that would be a circle, an ellipse, a parabola, a hyperbola. The 3D versions of those are called quadric surfaces. Use traces to sketch the quadric surface with equation x squared plus y squared over 9 plus z squared over 4 equals 1. So here's what we do. Basically, you're going to substitute in different values for z. So the first thing we're going to do is we're going to say, well, what happens when what happens if z equals 0? So if z equals 0, let's see here. So if z is equal to 0, then what we have is x squared plus y squared over 9 equals 1. And this is an ellipse, right? So this is going to be an ellipse, and it's going to come out 1 and 1, 2, 3. So it's an ellipse like that, right? And then we say, well, what happens if z is equal to, I don't know, what if z is equal to 2? So let's see here. So in these slides, let's just follow these slides. In general, the horizontal trace in the plane z equals k. So this is saying what happens if you substitute z equals k. Do you notice, what do we mean by this horizontal trace? So we're saying you're doing the cross section. This setting z equal to 0 means you're looking at the cross section of what happens in that xy plane. Okay? If you're looking at the trace of z equals 2, that means you're looking at the cross section for z equals 2. Right? So if you're, instead of going one by one, you can just take one or two cross sections, and then after that, generalize. So we say, what is the cross section if you plug in z equals k? And the answer is, well, now if we plug in z equals k, now we're going to solve for k. We get x squared plus y squared over 9 equals 1 minus k squared over 4. Okay? And in order to make this an ellipse, in order for this to make sense, first of all, 1 minus k squared over 4 can't be a negative number, right? We need it to be positive. And in order for that to happen, we need for k squared to be less than 4. So that means that k needs to be in between negative 2 and 2. And so if k is in between negative 2 and 2, remember these are our traces for z, that means that we have an ellipse. So just overall, we're at 2 and negative 2. That means we're going to have different types of ellipses, right? So we'll have different types of ellipses in between 2 and negative 2. And notice that we won't have any cross sections if we are above 2 or below negative 2. And then we can do similar computations to get the traces. What happens if we plug in x equals k? Now this means we're looking at cross sections that are parallel to the YZ plane, okay? And it turns out that we'll have these cross sections being ellipses as long as we are in between negative 1 and 1, okay? And then similarly, as long as y is in between negative 3 and 3. Now in this case, we're doing traces that are parallel to the XZ plane, okay? So then putting it all together, this is what it looks like. It's an ellipsoid because each cross section, now if we take a cross section that is horizontal, if we take a cross section that is vertical, and if we take a cross section that is vertical this way, right? We're getting ellipses each and every time. This is called an ellipsoid because all of its traces are ellipses. So it's symmetric with respect to the x, y, and z. And that's noted in the fact that the equation only includes even powers of x, y, and z. Okay. And now let's look here. We've got another example. Use traces to sketch the surface of z equals 4x squared plus y squared. Now, the approach, again, here is to look at traces. And first, we look at what happens if we plug in x equals 0. If we plug in x equals 0, then we get z equals y squared, right? So that means that our surface, right, for x equals 0, which is the same as the YZ plane, that means our surface is, our intersection, our cross section is a parabola. Okay, so that is for x equals 0. And then we can see, well, what happens if we put in another value for x? We're going to get z equals y squared plus 4k squared. That is a parabola, but it's going to be a parabola that is shifted up. So if here's y and here's z, we'll have a parabola that's shifted up 4k squared. So we're getting parabolas that are shifted up, right? So the bigger k is, the higher our parabola is shifted up. And if our k is negative, we've got symmetry here. So we've got an idea of these parabolas that are getting higher and higher. Does that make sense? I just wanted to kind of show you here. Do you see how we've got a parabola this way? But now if we move out to what happens here at x equals 1, we'll have another parabola, but it's higher and higher. Do you see we'll have parabolas that are lifted higher and higher? And we've got symmetry here, okay? And we similarly do that same type of analysis with traces in the horizontal plane parallel to the xz plane. Right, so if y equals k, we get other parabolas. So in our picture here, we would just have parabolas facing another way, right? So you've got parabolas this way. And then if z is a constant, z equals k, then first of all, z can only be positive. And second of all, we'll have our traces as ellipses. So now imagine that you're coming through and you've got ellipses here. So here's the idea. Imagine you've got a set of ellipses, but you also have parabolas that are going this way. And you also have parabolas that are in the y direction. So it's putting them all together gives you this shape here that is better manifested here. Okay, an elliptic paraboloid. Okay, so I'm going to, this is very similar, this example here, sketching the surface z equals y squared minus x squared. And you look at the traces. Now notice here what they're doing is they're including we're doing the traces in 2 dimensions, right? So it's kind of easier to see. And now to get the idea of the 3rd dimension, you take those traces and you kind of concatenate them, okay, to get an idea of what the traces look like all together. And this is called a hyperbolic paraboloid, aka saddle. Okay. And so the deal here is that notice that if we look at our cross sections, our vertical, will this be? No, horizontal cross section is going to be hyperbola. Okay. But if we look at a cross section this way, we'll get parabolas that are facing upside down. Does that make sense? We'll have parabolas facing upside down. Right? And then like what's holding them all together is this hyperbola. Okay. And so I'm going to, again, we're going to skip forward, and this is what we're going to be focusing on. Now, this chart right here is in your textbook, and this is, again, because we're in 12.6. And what we're going to do is we're going to practice, and we're going to learn how to create these surfaces, how to draw these surfaces with Mathematica. And we'll probably do that now that I think about it, we might do that actually this Thursday. This is a good time because we're at the end of the chapter, right? So we'll learn how to draw these using Mathematica, but also make sure that you are practicing using traces to sketch these surfaces as well. Okay, and this is a little chart here that can be found in your textbook. All right, that's it.